For most of human history, the center of our galaxy was nothing more than a mystery hidden behind veils of dust and distance. Ancient peoples looked up at the glowing band of the Milky Way stretching across the night sky, never knowing that at its heart, 26,000 light-years away, lurked one of the most extreme objects in the universe. A monster so massive that it weighs as much as 4 million suns, yet so compact that it could fit within the orbit of Mercury, the closest planet to our Sun. To put this in perspective, if you could somehow shrink all that mass down, it would create a sphere of such intense gravity that even light itself cannot escape a prison of space-time from which there is no return. A cosmic predator that bends space and time itself, from which nothing can escape once it crosses the point of no return. Imagine a whirlpool in the fabric of reality itself, where the normal rules of physics break down and time can slow to a crawl. Where a year for someone far away might pass as mere seconds for something falling toward the abyss, where up and down, past and future lose their familiar meanings. This is Sagittarius A, the supermassive black hole at the center of our galaxy. It is invisible, yet its presence shapes the orbits of millions of stars. Silent for the most part, it occasionally roars with bursts of radiation that can be detected across the electromagnetic spectrum, defying our everyday understanding of reality. It exists as a tear in the fabric of space-time itself, a place where Einstein's equations predict that matter compresses to infinite density and the curvature of space becomes infinite. For decades, scientists pursued this phantom, tracking the motions of stars that danced around an invisible partner, building Earth-sized telescopes to capture its shadow, and testing the very laws of physics in the most extreme environment accessible to us. The journey to understand Sagittarius A has been one of persistence, ingenuity, and wonder, forcing us to confront the limits of our knowledge and pushing the boundaries of what is possible in observational astronomy. What secrets does this black hole hold? How does it influence our galaxy? What would happen if we could journey to its edge? What does its existence tell us about the nature of space, time, and reality itself? The answers to these questions reveal not just the story of a black hole, but the story of our galaxy, our universe, and the fundamental laws that govern all of existence. Long before anyone suspected a black hole lurked at the heart of the Milky Way, astronomers struggled with a more basic question: where exactly was the center of our galaxy? For centuries, humans had observed the luminous band of light stretching across the night sky, never fully understanding what they were seeing. Some thought it was a ring of clouds glowing in reflected light. Others believed it was an accumulation of distant stars, too faint individually to resolve, but collectively forming a river of light across the heavens. None could say with certainty what lay at its core, or even where that core might be located. As telescopes improved and photographic techniques advanced in the early 20th century, astronomers began the painstaking work of mapping the three-dimensional structure of our galaxy. This was no simple task. Unlike external galaxies, which can be viewed from the outside and whose spiral structures are immediately apparent, we live inside the Milky Way. Trying to map our galaxy from within is like trying to draw a map of a forest while standing in the middle of it, surrounded by trees that block your view in every direction. In the 1920s, astronomers made a revolutionary discovery that would reshape our understanding of our place in the cosmos. By studying globular clusters, dense, spherical collections of hundreds of thousands of ancient stars that orbit the Milky Way like satellites, and measuring their distances using special stars called Cepheid variables as cosmic measuring sticks, they determined that these clusters formed a spherical halo around a distant point in space. This point, they realized, must be the true center of the galaxy. The discovery was both humbling and profound. Our solar system was not at the center of the galaxy as many had assumed. Instead, we orbited far out in the galactic suburbs, roughly 26,000 light-years from the true center. This was yet another step in humanity's long journey of cosmic demotion. First, Copernicus showed that Earth was not the center of the solar system. Then, it became clear that the Sun was just one star among billions. Now, this discovery revealed that even our Sun occupied no special place within the galaxy, relegated to an ordinary position in the outer disk. Everything changed with the development of radio astronomy in the 1930s and 40s. This new field began when engineers at Bell Telephone Laboratories discovered radio waves coming from the galactic center while investigating sources of static that interfered with telephone communications. It was a serendipitous discovery that would revolutionize astronomy. Radio waves, unlike visible light, can pass through dust clouds with ease. Their longer wavelengths allow them to navigate around the tiny dust grains that block shorter wavelength optical light, much like how you can hear someone talking around a corner but can't see them. When astronomers turned their new radio telescopes towards Sagittarius in the following decades, they found not darkness, but a complex and brilliant radio landscape. The galactic center blazed with emissions, suggesting the presence of energetic processes unlike anything seen elsewhere in the galaxy. As radio surveys became more detailed through the 1950s and 60s, astronomers mapped an increasingly complex structure at the galactic center. They found extended clouds of ionized gas, glowing in radio wavelengths. They discovered supernova remnants, the expanding shells of debris from stellar explosions. They identified regions of intense star formation, where new stars were being born from collapsing gas clouds. The galactic center was not a quiet, empty place, but a dynamic, violent, and active region of the galaxy. Amid all this complexity, one source stood out. Compact, incredibly bright in radio wavelengths, and appearing to mark the exact gravitational center of the galaxy, this mysterious object seemed unlike anything else in the galactic center. It was clearly something extraordinary, something that demanded explanation, but what could it be? In February of 1974, two astronomers were using a specialized radio telescope system at the National Radio Astronomy Observatory in Green Bank, West Virginia, to study the galactic center in unprecedented detail. They were using a technique called interferometry, which combines signals from multiple telescopes to achieve far sharper images than any single telescope could produce, like using two eyes instead of one to perceive depth. The astronomers were initially interested in studying star-forming regions near the galactic center, particularly a giant cloud of molecules. After observing this cloud on February 13th and 15th, they decided, somewhat on impulse, to point their instruments directly at the galactic center itself. What they found was remarkable: an extremely compact radio source with an intense signal far more powerful than expected. The source was tiny, bright, and appeared to sit at the very heart of the galaxy. They had discovered something momentous, though its true nature remained unclear. The two young astronomers were cautious in their initial scientific paper. They described the source and its properties, but avoided making bold claims about what it might be. In the competitive world of astronomy, being wrong about something as fundamental as the nature of the galactic center could be career-ending. Better to present the observations and let the evidence accumulate. The discovery needed a name. For nearly a decade, various designations were proposed. Then, in 1982, one of the astronomers had an inspiration. He remembered his doctoral work in atomic physics, where excited energy states of atoms were denoted with an asterisk, the times symbol. The radio source they had discovered was certainly exciting. In both the everyday and technical sense, it was energizing the entire galactic center region, much like an excited atom emits energy to its surroundings. He proposed the name Sagittarius A, denoting the source as the most significant radio emitter, in the larger Sagittarius A complex. The name stuck and would become one of the most important designations in astronomy. But the name was just the beginning. Understanding what Sagittarius A actually was would take decades of patient observation and theoretical work. Early theories about the nature of Sagittarius A varied widely, reflecting the exotic and extreme conditions at the galactic center. Some astronomers suggested it might be a dense cluster of stars, perhaps millions of stars packed so tightly together that they appeared as a single point source in radio observations. The combined radio emission from so many stars might, in theory, produce the observed signal. Others proposed it could be a massive cloud of hot, ionized gas heated by radiation from nearby stars. A few scientists began entertaining a more exotic possibility. What if Sagittarius A was a black hole? The idea seemed almost too fantastic. Black holes were still relatively new concepts in astronomy, hovering somewhere between respectable physics and science fiction. The term itself had only been coined in 1967. While the theoretical foundations of black holes were solid, based on Einstein's general theory of relativity, actual observational evidence for their existence remained sparse and controversial. The concept of black holes had a long and winding history in theoretical physics. The mathematical foundation was laid remarkably early, in 1916, when a physicist found an exact solution to Einstein's equations just months after Einstein published his general theory of relativity. This solution described the gravitational field around any spherical object. Within this solution lurked something deeply strange and unsettling. A boundary at a certain radius where the escape velocity, the speed needed to break free, would equal the speed of light. This radius represented a point of no return. Inside this boundary, nothing could escape, not even light itself. The mathematics seemed clear, but the physical interpretation was deeply troubling. Could such objects really exist? For decades, these mathematical curiosities remained just that. Curiosities studied by theorists, but not taken seriously as physical objects that might actually exist in nature. Many physicists, including Einstein himself, doubted that nature could produce such bizarre objects. Surely something would intervene to prevent the formation of these singularities where matter was crushed to infinite density and space-time itself became infinitely curved. The equations might predict black holes, but perhaps the equations were simply being pushed beyond their domain of validity. Theoretical work through the 1950s and 60s gradually changed this perspective. Physicists proved that black holes were not just mathematical artifacts, but inevitable consequences of general relativity. When a sufficiently massive star exhausted its nuclear fuel and collapsed, no known force could halt the implosion. The collapse would continue until a singularity formed, hidden behind an event horizon from which nothing could escape. Black holes, the mathematics insisted, had to exist. By the 1980s and 90s, the black hole hypothesis for Sagittarius A had gained serious traction among astronomers. Several independent lines of evidence pointed toward this conclusion. First, there was the extraordinary compactness of the radio source. Observations constrained its size to be smaller than our solar system, yet radio emissions and other evidence suggested an enormous mass concentrated in this tiny volume. No ordinary object, not even a dense cluster of stars, could be so compact without collapsing into a black hole. Second, observations in infrared wavelengths, which, like radio waves, could penetrate the galactic center dust, began revealing something remarkable. Stars near the galactic center were moving at extraordinary velocities. These weren't the sedate orbital speeds typical of stars elsewhere in the galaxy. These stars were screaming through space at velocities of thousands of miles per second, speeds that could only be explained if they were orbiting something with truly immense gravitational pull. and that something had to be concentrated in a very small region, right at the location of Sagittarius A. The evidence grew stronger with each passing year. Alternative explanations were proposed and carefully examined, but one by one they failed to match the observations. Could Sagittarius A be a cluster of neutron stars, the collapsed cores of dead stars, or stellar mass black holes packed tightly together? Detailed calculations showed that such a cluster would be unstable. Gravitational interactions between the objects would cause the cluster to fly apart or collapse into a single object within just a few million years. Far too short a time compared to the age of the galaxy. Could it be a ball of exotic dark matter, the mysterious invisible substance that makes up most of the matter in the universe, supported against collapse by unknown physics? This idea faced multiple problems. Dark matter doesn't interact strongly with normal matter, except through gravity, so it couldn't produce the observed radio emissions, X-rays, and infrared flares that Sagittarius A exhibited. And even if dark matter could somehow be confined to such a small region, it would likely be unstable. The challenge facing astronomers was clear. How do you prove the existence of something you cannot see? A black hole, by its very nature, emits no light. The event horizon, the boundary of no return, is a perfect information barrier. Nothing that crosses it can ever send a signal back to the outside universe. Observing a black hole directly seemed, if not impossible, then extraordinarily difficult. Instead, astronomers would need to rely on indirect methods, observing the effects of the black hole on its surroundings. They would need to watch stars orbiting the invisible object, mapping their trajectories with exquisite precision. They would need to observe the glow of hot gas spiraling toward the event horizon, heated by friction to millions of degrees. And they would need patience, lots of patience, because unraveling the mystery of Sagittarius A would take decades of careful observation. To truly understand Sagittarius A, we must first grasp what a black hole actually is at a fundamental level. This requires venturing into the strange world of general relativity, where our everyday intuitions about space and time break down completely. In our ordinary experience, space is a fixed, unchanging backdrop against which events unfold. Time flows steadily from past to future. Gravity is simply a force that pulls objects together. But Einstein showed that this picture is fundamentally wrong. In general relativity, space and time are not separate entities, but form a unified four-dimensional fabric called space-time. This fabric is not rigid but flexible, capable of being bent and warped by the presence of matter and energy. Imagine placing a bowling ball on a stretched rubber sheet and watching it create a depression. What we perceive as gravity is actually the curvature of space-time. Massive objects like stars and planets create depressions in the space-time fabric, and other objects moving through this curved space-time follow the contours of these depressions, which we interpret as gravitational attraction. Near ordinary objects like Earth or the Sun, space-time curvature is gentle. The effects of general relativity are subtle, producing only tiny deviations from the predictions of Newton's classical theory of gravity. But near extremely dense objects, space-time curvature becomes dramatic. And at a black hole, space-time curvature becomes so extreme that it creates a region from which nothing can escape. A black hole forms when matter becomes compressed to such extraordinary densities that the escape velocity from its surface exceeds the speed of light. The escape velocity is the speed needed to break free from an object's gravitational pull. Think of how fast a rocket must travel to leave Earth's surface. From Earth's surface, the escape velocity is about 25,000 miles per hour. From the Sun's surface, it's much higher. But from the surface of a black hole's event horizon, the escape velocity exceeds 186,000 miles per second, the speed of light itself. Since nothing can travel faster than light, a fundamental speed limit built into the laws of physics. Nothing can escape from inside a black hole's event horizon. Photons of light emitted inward or parallel to the horizon fall back toward the center. The event horizon marks an absolute boundary between the observable universe and the interior of the black hole. For stellar mass black holes, those formed from collapsed stars, this process is well understood. When a massive star, one with more than about 20 times the mass of the Sun, exhausts its nuclear fuel, it faces a crisis. Throughout its life, the star has been supported against gravitational collapse by the outward pressure generated by nuclear fusion in its core, where hydrogen atoms fuse into helium and release tremendous energy. When the fuel runs out, this pressure support disappears. The core implodes catastrophically, collapsing in a fraction of a second. The outer layers of the star fall inward and then rebound, generating a supernova explosion that can briefly outshine an entire galaxy. But the core continues collapsing, crushing matter to densities beyond anything found elsewhere in nature. If the core is massive enough, no known force can halt this collapse. The collapse continues until all the mass is concentrated in a vanishingly small region, what physicists call a singularity, where density becomes infinite and classical physics breaks down completely. Around this singularity, an event horizon forms, with a size determined solely by the mass of the collapsed core. Supermassive black holes like Sagittarius A are an entirely different phenomenon. With masses ranging from hundreds of thousands to billions of times that of the Sun, they cannot possibly form from the collapse of a single star. No star has ever existed or could ever exist with millions of solar masses. These behemoths must form through different mechanisms, and understanding these formation processes remains one of the great challenges in astrophysics. Several theories exist for how supermassive black holes form. Perhaps they grew gradually over billions of years, starting from smaller seed black holes left over from the first generation of stars in the early universe. These seeds would slowly accumulate mass by consuming nearby gas and merging with other black holes, gradually growing into the supermassive monsters we see today. Alternatively, in the chaotic early universe, massive gas clouds might have collapsed directly into supermassive black holes without ever forming stars. The truth likely involves a combination of these processes, with different supermassive black holes having different formation histories. Regardless of how they form, supermassive black holes share certain fundamental properties with their stellar mass cousins. They have event horizons from which nothing can escape. They warp space-time dramatically. They can consume matter from their surroundings, and when they do, they shine brightly as the infalling material heats up and emits radiation. Remarkably, the physics governing black holes is quite simple. A black hole is completely characterized by just three numbers: its mass, its electric charge, which is almost always negligible, and its angular momentum or spin. For Sagittarius A, the mass has been determined with impressive precision through decades of observations, 4.15 million times the mass of our Sun, with an uncertainty of just a few percent. The event horizon has a diameter of approximately 12 million miles, or about 19 million kilometers. To put this in perspective, that is roughly 17 times the diameter of the Sun, enormous by everyday standards, but tiny compared to the galaxy itself. If you could somehow transport Sagittarius A to our solar system and place it where the Sun is, its event horizon would extend about 1/6 of the way to Earth's orbit. Mercury, the innermost planet, would orbit comfortably outside the event horizon, though it would be doomed by the intense tidal forces and radiation. What happens at the event horizon is one of the most fascinating and counterintuitive aspects of black hole physics. Imagine an unfortunate astronaut falling into a black hole. For this astronaut, crossing the event horizon would be, in principle, entirely unremarkable. At the moment of crossing, they would feel nothing unusual. There is no wall, no barrier, no physical sensation of passing through anything special. They would simply continue falling, accelerating ever faster toward the center. The laws of physics, as they experience them, would remain unchanged. Looking around, they might even still see the stars behind them, though increasingly distorted and blue-shifted. Transmitted would be trapped just like them, falling inexorably inward. From their perspective, they could still send signals backward along their trajectory, but those signals would simply fall faster than they do, racing ahead toward the center. The direction they think of as outward has become, in a very real sense, backward in time. Just as you cannot travel backward in time in normal space-time, you cannot move outward from inside an event horizon. The future is now inward, toward the singularity, and there is no escaping that destiny. Before reaching the event horizon, however, our falling astronaut would face another deadly challenge: tidal forces. These are the differences in gravitational pull between their head and their feet, between their left and right sides. For a supermassive black hole like Sagittarius A, these tidal forces remain manageable. Even at the event horizon, you could theoretically cross alive. But as you fell deeper, the tidal forces would grow exponentially. Eventually, they would stretch you vertically and compress you horizontally in a process physicists grimly call spaghettification. Your body would be pulled into a long, thin strand, torn apart atom by atom. For smaller black holes, this fate would arrive even before you reached the event horizon. But there would be one crucial difference. They could never send a signal back out. Any light they emitted, any radio waves they transmitted, would be trapped just like them, falling inexorably inward. From their perspective, they could still send signals backward along their trajectory, but those signals would simply fall faster than they do, racing ahead toward the center. The direction they think of as outward has become, in a very real sense, backward in time. Just as you cannot travel backward in time in normal space-time, you cannot move outward from inside an event horizon. The future is now inward, toward the singularity, and there is no escaping that destiny. Before reaching the event horizon, however, our falling astronaut would face another deadly challenge: tidal forces. These are the differences in gravitational pull between their head and their feet, between their left and right sides. For a supermassive black hole like Sagittarius A, these tidal forces remain manageable. Even at the event horizon, you could theoretically cross alive. But as you fell deeper, the tidal forces would grow exponentially. Eventually, they would stretch you vertically and compress you horizontally in a process physicists grimly call spaghettification. Your body would be pulled into a long, thin strand, torn apart atom by atom. For smaller black holes, this fate would arrive even before you reached the event horizon. From the perspective of an observer safely outside the black hole watching this unfortunate astronaut fall in, the situation appears very different. As they watch the falling person approach the event horizon, they would see them moving slower and slower, their image becoming increasingly reddened as the light climbing out of the gravitational well loses energy. Time itself runs slower in stronger gravitational fields, a real effect that's been measured countless times, and near the event horizon, this gravitational time dilation becomes extreme. The outside observer would see the astronaut approach the horizon asymptotically, never quite reaching it, their image growing dimmer and redder until it faded into invisibility. To them, the falling person would appear to freeze at the event horizon, suspended forever at the moment of crossing, though in reality, from the astronaut's perspective, they crossed smoothly and continued falling. A black hole in isolation would be truly invisible. A literal hole in space, emitting no light and detectable only through its gravitational effects on passing starlight or orbiting objects. But Sagittarius A is far from isolated. It sits at the heart of our galaxy, in a crowded, dynamic region filled with stars, gas clouds, and interstellar debris. Some of this material drifts close enough to the black hole to be captured by its gravitational pull, and when matter falls toward a black hole, remarkable things happen. The key to understanding this process is angular momentum, essentially, rotational motion. Very rarely does material fall straight toward a black hole. More typically, the material has some sideways motion that causes it to swing past the black hole rather than plunging directly in. As this material falls, conservation of angular momentum, a fundamental law of physics, like conservation of energy, causes it to swing around the black hole, gradually spiraling inward. The result is an accretion disk, a swirling vortex of matter orbiting the black hole and slowly feeding it, like water spiraling down a drain. As material in the accretion disk spirals inward, it speeds up and compresses, generating tremendous friction. This friction heats the disk to extreme temperatures, millions or even billions of degrees in the innermost regions, just outside the event horizon. At these temperatures, the material doesn't behave like ordinary gas. The atoms are completely ionized, stripped of their electrons to form what's called a plasma. This superhot plasma emits radiation across the entire electromagnetic spectrum, from radio waves through visible light to X-rays and potentially gamma rays. For Sagittarius A, however, the accretion disk is relatively sparse and inefficient. The black hole is, in astronomical terms, essentially starving. Current estimates suggest that Sagittarius A consumes only about 1 Earth mass of material every few thousand years. This is an extraordinarily low rate for a supermassive black hole. More actively feeding black holes, particularly those in distant quasars, extremely bright galaxies powered by supermassive black holes, can consume thousands of times the mass of the Sun every year. Shining so brightly, they outshine their entire host galaxies by a factor of 100 or more. Why is Sagittarius A so underfed? The answer lies in the nature of the material surrounding it. The gas in the galactic center is generally hot and tenuous, meaning sparse and low density, and it's moving fairly rapidly. This gives the gas a lot of thermal pressure and angular momentum, making it difficult for the gas to lose enough energy and angular momentum to actually fall into the black hole. Much of the gas that approaches Sagittarius A simply orbits around it or is blown away by stellar winds and radiation pressure before ever crossing the event horizon. This creates what astronomers call a radiatively inefficient accretion flow, or RIAF. Physicists love acronyms. In this regime, the accreting material is so hot and tenuous that it radiates away only a small fraction of its energy before falling into the black hole. The gas remains puffed up, forming a geometrically thick but optically thin accretion flow rather than a thin, dense disk. Most of the gravitational potential energy released by the infalling material goes into heating the gas rather than producing radiation. The result is a dim, relatively quiet black hole, nothing like the brilliant quasars seen in more distant galaxies where conditions are very different. Surrounding the accretion disk is another crucial component, the corona. This is a region of extremely hot, tenuous plasma that extends around and perhaps above the accretion disk, somewhat like the Sun's corona, the glowing atmosphere visible during a solar eclipse. In this corona, temperatures reach tens or even hundreds of millions of degrees, far hotter than the disk itself. At these temperatures, the plasma emits primarily in X-rays, and indeed, X-ray observations are crucial for studying the corona around Sagittarius A. The corona appears to be highly variable, flickering and changing on timescales of minutes to hours. These variations provide important clues about the physical processes happening close to the event horizon. The X-rays are thought to be produced when hot electrons in the corona collide with lower energy photons from the accretion disk and boost them up to X-ray energies, a process called inverse Compton scattering. By studying the timing and spectral properties of these X-rays, astronomers can probe the geometry and physics of the innermost regions around the black hole. Magnetic fields play an absolutely crucial role in the accretion process. The plasma falling towards Sagittarius A is ionized and therefore threaded with magnetic field lines. These fields are generated and amplified within the disk itself through what's called a dynamo process. Differential rotation, the inner parts of the disk rotating faster than the outer parts, stretches and twists field lines, amplifying them, while turbulence tangles them into complex configurations. The result is a disk permeated by strong, tangled magnetic fields. These magnetic fields do much more than just exist. They transport angular momentum outward through the disk, allowing material to lose energy and spiral inward. Essentially, the magnetic fields provide the friction that makes accretion possible. They can also launch powerful outflows and jets perpendicular to the disk, though for Sagittarius A these jets are weak or perhaps absent. The exact role of magnetic fields in accretion remains an active area of research, with sophisticated computer simulations attempting to capture the complex interplay between magnetic fields, turbulence, and the intense gravity near the black hole. Many supermassive black holes, particularly those in distant quasars and active galaxies, produce spectacular relativistic jets, narrow beams of matter and energy that stream away from the black hole's poles at speeds approaching the speed of light. Jets can extend for thousands or even millions of light years, vastly longer than the galaxy hosting the black hole. They pump enormous amounts of energy into the surrounding space, heating gas, triggering star formation in some places while suppressing it in others, and shaping the evolution of entire galaxy clusters. Sagittarius A, however, shows only minimal jet activity. While there is some evidence for a weak, compact outflow extending perhaps a few light years from the black hole, it is nothing compared to the monster jets seen in galaxies with names like M87, Centaurus A, or Cygnus A. The absence of strong jets from Sagittarius A tells us something important. The black hole is not actively feeding, and the conditions necessary for producing powerful jets are not currently met. The production of jets requires two key ingredients working together: a rapidly spinning black hole and a strong, organized magnetic field threading through the accretion disk and extending out to the black hole's poles. The spin of the black hole twists the magnetic field lines through a process called frame dragging, where the rotating black hole literally drags space-time around with it. Imagine honey swirling around a spoon. This twisting action winds up the magnetic field and can launch material outward along the field lines in tightly collimated beams. For Sagittarius A, it appears that either the accretion rate is too low or the magnetic field is not sufficiently strong and organized to produce powerful jets. The black hole almost certainly spins. Most supermassive black holes accumulate significant angular momentum over their lifetimes through the gradual consumption of material that has its own rotation. But the sparse, disorganized accretion flow means the conditions for jet production are not met. This was not always the case. Multiple lines of evidence suggest that Sagittarius A was far more active in the past, perhaps even producing significant jets or outflows during periods of more vigorous feeding. The most dramatic evidence comes from structures called the Fermi bubbles, discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope. These are two enormous lobes of gamma ray emitting gas gamma rays, being the highest energy form of light. Extending roughly 25,000 light-years above and below the galactic plane, comparable to the distance from the Sun to the galactic center itself. The Fermi bubbles are thought to be remnants of a massive outburst from Sagittarius A that occurred approximately 6 to 10 million years ago. During this event, the black hole likely experienced a major feeding episode, consuming a large gas cloud or perhaps multiple stars. The resulting explosion, whether a jet or a powerful wind, drove vast amounts of gas out of the galactic center, inflating these enormous bubbles. The shock waves from this outburst heated the gas and accelerated particles to high energies, producing the gamma-ray emission we observe today. The absence of strong jets from Sagittarius A today is actually fortunate for life in our galaxy. If the black hole were actively feeding and producing powerful jets, as happens in quasars and active galactic nuclei, the radiation environment in the inner galaxy would be incredibly harsh. Planets within thousands of light-years of the galactic center would be bathed in intense X-rays and gamma rays, potentially sterilizing them and making the development of complex life extremely difficult or impossible. Our position far out in the galactic disk, combined with the relative quietness of Sagittarius A, may be among the factors that have allowed complex life to develop on Earth. The most direct and compelling evidence for Sagittarius A's existence comes not from the black hole itself, which remains invisible, but from the stars that orbit around it. These stars are among the most extraordinary objects in our galaxy, moving at velocities and experiencing gravitational forces found nowhere else in the Milky Way. Tracking them required patience, precision, and decades of dedication by teams of astronomers who devoted their careers to watching these cosmic dances unfold. Beginning in the early 1990s, two independent teams embarked on what would become one of the longest-running and most successful observing campaigns in the history of astronomy. One team worked primarily with the European Southern Observatory's facilities in Chile. The other used the powerful twin telescopes of the W.M. Keck Observatory in Hawaii. The leaders of both teams would later share the 2020 Nobel Prize in Physics for this groundbreaking work. Both teams had the same goal: to track individual stars in the crowded galactic center and measure their motions with unprecedented precision. This required overcoming formidable observational challenges. The galactic center is densely packed with stars, making it difficult to resolve individual objects. Imagine trying to spot individual fireflies in a dense swarm. The dust obscuring the center blocks visible light, requiring observations in infrared wavelengths. And Earth's atmosphere constantly blurs and distorts images through a shimmering effect similar to what you see above a hot road on a summer day, making precise measurements nearly impossible without sophisticated technology. The breakthrough came with adaptive optics, a technology that revolutionized ground-based astronomy in the 1990s. Adaptive optics systems use deformable mirrors that can change shape hundreds of times per second, compensating for atmospheric turbulence in real time. By measuring how the atmosphere distorts light from a bright reference star and rapidly adjusting the mirror to cancel those distortions, adaptive optics can produce images nearly as sharp as those from space-based telescopes, essentially. It removes the twinkle from starlight. With adaptive optics and sensitive infrared cameras, both teams could finally resolve individual stars in the galactic center and track their positions over time. What they found was astonishing. Many stars near the galactic center moved at extraordinary velocities, their positions changing noticeably from year to year and sometimes even from month to month. These were not the sedate orbital motions typical of stars elsewhere in the galaxy. These stars were racing through space at thousands of miles per second, driven by the gravitational pull of something massive and invisible at the precise location of the radio source Sagittarius A. Among all the stars tracked in these surveys, one in particular stands out. Designated S2 by the European team and S0-2 by the American team. Both names are used in the scientific literature. This star would become perhaps the most important single star in the history of black hole astronomy. S2 is a hot, blue main sequence star with about 14 times the mass of the Sun and a surface temperature exceeding 36,000 degrees Fahrenheit, hot enough to glow blue-white. Young by stellar standards, perhaps only a few million years old, S2 shines with the brightness of thousands of suns combined. But what makes S2 truly extraordinary is its orbit. The star follows an extremely elongated elliptical path that brings it shockingly close to Sagittarius A at its nearest approach, called periapsis in astronomical terminology. At periapsis, S2 comes within about 17 light-hours of the black hole, roughly 120 times the distance from the Sun to Earth, or about 4 times the distance from the Sun to Neptune. This might sound like a safe distance, but for an orbit around a supermassive black hole, it's breathtakingly close, well within the region where relativistic effects become significant. S2's orbital period is approximately 16 years, remarkably short for an orbit around the galactic center. Most stars in the central region take thousands, tens of thousands, or even millions of years to complete a single orbit. But S2 screams around the black hole in less time than it takes a child to graduate high school. At periapsis, the star reaches velocities approaching 4,750 miles per second, or roughly 2.5% of the speed of light. That's fast enough to circle Earth's equator in about 5 seconds, or travel from the Earth to the Moon in less than a minute. The first complete orbit of S2 observed from start to finish took place between the early 1990s and 2002. As the orbit closed, with the star returning to nearly the same position it had occupied a decade and a half earlier, both teams could finally calculate with confidence the mass of the object S2 was orbiting. The answer was unambiguous and stunning. Approximately 4 million solar masses concentrated in a region no larger than our solar system. This was the smoking gun evidence that finally convinced the broader scientific community that Sagittarius A was indeed a supermassive black hole. But S2 was not alone. Over the years, both teams discovered more and more stars on similar orbits, though most with longer periods and less extreme closest approaches. Today, astronomers have tracked more than 40 so-called stars with well-determined orbits around Sagittarius A. Each additional orbit provided an independent measurement of the central mass, and remarkably, all the measurements agreed within observational uncertainties. The pattern was clear and consistent. Dozens of stars, all orbiting the same invisible point with orbital properties that allowed independent calculations of a central mass. The current best estimate, based on decades of observations and sophisticated orbital modeling, places the mass of Sagittarius A at 4.15 million solar masses with an uncertainty of less than 3%. This is one of the most precise measurements of any supermassive black hole in the universe. More precise, in fact, than our measurement of many much closer objects. The extreme velocities and strong gravitational fields experienced by the stars, especially during their closest approaches, create ideal conditions for testing Einstein's general theory of relativity. Near Sagittarius A, gravity is strong enough and velocities high enough that relativistic effects become measurable. These stars are moving fast enough and experiencing gravity intense enough that the predictions of general relativity differ measurably from those of Newton's 300-year-old theory of gravity, which works perfectly well for everyday situations but breaks down in extreme conditions. During S2's closest approach in May of 2018, astronomers mounted intensive observing campaigns to detect these relativistic effects. Both teams used their largest telescopes equipped with the latest instruments, observing S2 as frequently as weather and scheduling permitted. The goal was to detect the gravitational redshift of light from S2, one of the key predictions of general relativity that had never before been tested for a star orbiting a supermassive black hole. Gravitational redshift occurs because photons climbing out of a gravitational well lose energy like a ball thrown upward, slowing down as it rises. According to general relativity, This loss of energy translates into a shift in the photon's wavelength toward longer, redder wavelengths, hence redshift. The effect had been measured before in laboratory settings and in our solar system, but never before for a star orbiting a supermassive black hole. During its 2018 closest approach, S2 was predicted to show a combined gravitational and velocity-based redshift equivalent to a velocity shift of about 125 miles per second. The results, published in late 2018 and refined in subsequent papers, confirmed the predictions of general relativity beautifully. The spectral lines in S2's light, the characteristic fingerprints of elements in the star's atmosphere, were redshifted by almost exactly the amount Einstein's theory predicted. Within the measurement uncertainties, there was no deviation from general relativity. Alternative theories of gravity that predicted different amounts of redshift could be ruled out. This was a triumph for both observational astronomy and for general relativity itself, showing that Einstein's century-old theory still accurately describes gravity even in these extreme conditions. Another prediction of general relativity being tested with S2 is orbital precession. In Newton's theory of gravity, a planet or star orbiting a single central mass traces out a perfect ellipse, returning to exactly the same closest approach point with each orbit. But general relativity predicts a slight rotation of the ellipse itself, causing the closest approach point to slowly shift with each orbit. This is the same effect that explains the anomalous precession of Mercury's orbit around the Sun, one of the first successful predictions of general relativity back in 1915. For S2, the predicted precession is much larger than for Mercury, about 12 arcminutes, 1/5 of a degree, per orbit, still tiny, but measurable. Over multiple orbits, this precession should cause S2's orbital ellipse to rotate noticeably, creating a rosette pattern rather than a closed ellipse. Detecting this precession requires tracking the star through multiple complete orbits, which is finally becoming possible after nearly 3 decades of observations. Early results suggest the precession is consistent with general relativity, though uncertainties remain larger than for the redshift measurement. As data accumulates over the coming decades, with S2 completing more orbits, the precession measurement will steadily improve, providing an even more stringent test of Einstein's theory. The stars raise an intriguing mystery. How did young, massive stars end up orbiting so close to a supermassive black hole? This question has puzzled astronomers since these stars were first discovered. Young stars like S2 form from the collapse of dense clouds of gas and dust. But the extreme tidal forces near Sagittarius A, the difference in gravitational pull between the near and far sides of an object, should prevent gas clouds from collapsing to form stars. The gravitational gradient across a cloud near the black hole would tear it apart before it could contract enough to ignite nuclear fusion and become a star. Several explanations have been proposed. One possibility is that these stars formed farther from the black hole and later migrated inward. Perhaps they formed in a massive star cluster several light-years from Sagittarius A, and gravitational interactions within the cluster ejected some stars on highly eccentric orbits that brought them close to the black hole. Think of it like a game of cosmic billiards, where collisions and near misses between stars occasionally send one flying off on an unusual trajectory. Another idea is that these stars were originally in binary systems, pairs of stars orbiting each other, and a close passage by the black hole disrupted the binary, capturing one star while ejecting the other at high velocity. Computer simulations show this process can indeed produce stars on orbits similar to what we observe for the stars. A more exotic possibility is that the stars formed in an accretion disk around the black hole itself. If Sagittarius A underwent a period of intense feeding in the not-too-distant past, consuming a massive gas cloud, the accreting material would have formed a dense disk around the black hole. Under the right conditions, this disk might have become gravitationally unstable and fragmented, with some fragments collapsing to form stars directly in orbit around the black hole. This would naturally explain why so many young stars are found on elongated orbits around Sagittarius A, all in roughly disk-like configurations. The truth may involve a combination of these processes, with different stars having different origins. Unraveling this mystery will require more observations, better theoretical models, and perhaps the discovery of even more stars on extreme orbits around the black hole. The environment in which the stars orbit is unlike anywhere else accessible to our telescopes. These stars experience gravitational accelerations billions of times stronger than Earth's surface gravity. During S2's closest approach, the gravitational acceleration is roughly 1.5 billion times stronger than what we experience on Earth's surface if you could somehow stand on a surface experiencing that acceleration, which you can't. But it's a useful thought experiment. You would be crushed instantly. The tidal forces, the difference in gravitational pull between the near and far sides of the star, are also substantial, though not yet strong enough to tear the star apart. A less massive or larger object at the same distance would be tidally disrupted, ripped into a streamer of gas. The radiation environment is also intense. While Sagittarius A itself is relatively dim, the high density of massive luminous stars in the central region creates a harsh radiation field. Any planet orbiting one of these stars would be bombarded by ultraviolet radiation and X-rays from thousands of nearby stars, making the development of life as we know it essentially impossible. Add to this the frequent supernova explosions from massive stars reaching the end of their lives and the occasional close stellar encounters, and the galactic center emerges as one of the most hostile environments in the galaxy. Despite these extreme conditions, the stars have persisted for millions of years. This tells us something important about the dynamics of the galactic center. The environment, while extreme, is not so chaotic that stars cannot maintain stable orbits for extended periods. The stellar density, while high, is not so extreme that collisions are frequent. The stars exist in a remarkable middle ground, close enough to the black hole to experience extreme relativity, but far enough away to avoid immediate destruction. The ultimate fate of the stars remains uncertain. Over millions of years, gravitational interactions with other stars will gradually alter their orbits. Some stars may have their orbits circularized, settling into less eccentric paths at larger distances from the black hole. Others may be perturbed onto even more eccentric orbits, eventually bringing them close enough to be tidally disrupted, literally torn apart by the black hole's gravity. Still others may receive gravitational kicks that eject them from the galactic center altogether, sending them flying through the galaxy as high-velocity stars traveling at thousands of miles per second. For S2 specifically, computer simulations suggest its orbit will remain relatively stable for at least several million years. But in the long term, perhaps tens or hundreds of millions of years from now, chance encounters with other stars or the gradual effects of general relativity will eventually alter its trajectory. S2 might be ejected from the galactic center, it might collide with another star, or it might spiral inward to be consumed by Sagittarius A in a spectacular tidal disruption event. When that day comes, if humanity or its descendants still exist and are still watching, they will witness one of nature's most spectacular displays, a star being torn apart by a black hole, briefly outshining the entire galactic center as the stellar debris heats up and emits furiously before crossing the event horizon. Surrounding Sagittarius A, within a sphere roughly 3 light-years in radius, lies one of the most remarkable concentrations of matter in the galaxy. This is the nuclear star cluster, a region containing approximately 10 million stars packed into a volume that, by galactic standards, is extraordinarily small. The stellar density here is roughly 1 million times higher than in our solar neighborhood. If our Sun were located in this central region instead of its current position far out in the galactic disk, the night sky would be transformed beyond recognition. Instead of seeing a few thousand stars with the naked eye, as we do from Earth on a clear, dark night, an observer on an Earth-like planet in the galactic center would see millions of stars. The brightest would shine as brilliantly as Venus at its brightest, but there would be thousands of such stars scattered across the sky. Imagine a night sky so crowded with brilliant stars that you could read a book by their collective light. The Milky Way's band would be invisible not because dust blocks it, but because it would be drowned out by the overwhelming number of nearby bright stars. Constellations as we know them would be meaningless. The patterns would shift noticeably over just a few human lifetimes as stars moved in their orbits. The nearest neighboring star would likely be less than a week away at light speed, compared to the 4-year journey to our nearest neighbor, Proxima Centauri. In practical terms, if you could travel at light speed, you could visit a neighboring star system and return home in less than a month. Close encounters and near collisions between stars, extraordinarily rare in our neighborhood, we expect none in the remaining lifetime of the Sun, would be common events on timescales of thousands or tens of thousands of years. Planetary systems would be frequently disrupted by passing stars, making stable long-term orbits the kind that allowed life to develop on Earth extremely rare or perhaps impossible. The nuclear star cluster is not just dense, but also remarkably diverse in its stellar populations. It contains stars of all ages, from ancient red giants formed billions of years ago when the galaxy was young, to hot blue giants that are only a few million years old stellar infants by cosmic standards. This mix of stellar ages tells a complex story of the cluster's history. It suggests multiple episodes of star formation interspersed with long periods of relative quiescence, a cycle of birth and dormancy playing out over billions of years. One of the most striking and puzzling features of the nuclear star cluster is the presence of those young, massive stars so close to Sagittarius A. As we discussed earlier with the stars, these stars are grouped into disk-like structures that orbit the black hole in organized patterns. One group, called the clockwise disk, contains dozens of young stars all orbiting in roughly the same plane with similar directions. Another group, the counterclockwise disk, orbits in the opposite direction like two merry-go-rounds spinning in opposite directions around the same center. The existence of these organized disks was entirely unexpected. In such a chaotic, crowded environment, astronomers expected stellar orbits to be randomized by gravitational interactions, with stars moving in all directions with no preferred orientation, like a swarm of bees. Instead, these disks suggest that the young stars formed together in a coordinated manner, perhaps from a single massive gas cloud that fell into the galactic center, flattened into a disk, like pizza dough being spun, and then fragmented into stars. In addition to the young massive stars and the ancient red giants, the nuclear star cluster contains vast numbers of lower mass stars that are much harder to observe individually. These include main sequence stars similar to the Sun, though generally older and enriched with heavy elements from previous generations of stars. Red dwarfs, the faintest and longest-lived stars in the universe, which could persist for trillions of years, and compact stellar remnants like white dwarfs, the dense cores of dead sun-like stars, neutron stars, the collapsed cores of massive stars, and stellar mass black holes. Theoretical models predict that the nuclear star cluster should contain hundreds or even thousands of stellar mass black holes gradually sinking towards Sagittarius A through a process called dynamical friction. When a massive object moves through a sea of lighter objects, like a whale swimming through a school of fish, gravitational interactions cause it to lose momentum and sink toward the center of the system. Over millions of years, stellar mass black holes born in the galactic center should sink inward, accumulating around Sagittarius A in a dense concentration. These stellar mass black holes, though individually invisible, could have important effects on the dynamics of the nuclear star cluster. Their gravitational influence could perturb the orbits of visible stars, potentially explaining some of the orbital peculiarities observed in the stars. Occasionally, two stellar mass black holes might merge, producing gravitational waves ripples in spacetime itself, detectable by observatories like LIGO, the Laser Interferometer Gravitational Wave Observatory. And in the very long term, some of these stellar mass black holes will eventually be captured by Sagittarius A, falling in to add their mass to the supermassive black hole in brief bursts of gravitational wave emission. Stellar collisions, though rare in most parts of the galaxy, are significantly more common in the nuclear star cluster due to the high stellar density. In our solar neighborhood, stellar collisions are so rare that we expect none to occur within any given volume of space over the entire age of the universe. But in the crowded nuclear star cluster, collisions are far more likely. When two stars collide, they typically merge, forming a single more massive star. These collision products can have unusual properties, appearing younger than they should be for their mass or having anomalous chemical compositions. Some of the strange stars observed in the galactic center might be the products of such collisions. The nuclear star cluster is not static, but constantly evolving through a complex interplay of processes. Stars form in bursts when gas falls into the central region. Massive stars live brief lives, just a few million years, and explode as supernovae, enriching the surrounding medium with heavy elements and heating the gas. Stellar winds from massive stars and planetary nebulae, the gently expelled outer layers of dying sun-like stars, return material to the space between stars. Gravitational interactions shuffle stellar orbits, causing some stars to sink inward and others to be ejected. And all the while, the black hole at the center slowly accretes material, growing imperceptibly larger with each passing millennium. Just beyond the nuclear star cluster, roughly 1.5 to 7 light-years from Sagittarius A, lies another crucial structure, the circumnuclear disk, or CND. This is a donut-shaped collection of molecular gas and dust, containing tens of thousands of times the mass of our Sunday. Unlike the stars in the nuclear cluster, which orbit on timescales of hundreds to millions of years, the gas in the circumnuclear disk rotates around the black hole in a more organized fashion. Though the disk itself has a complex, clumpy structure with distinct streamers and cavities, the circumnuclear disk represents the closest significant reservoir of gas to Sagittarius A, making it potentially important for feeding the black hole. However, most of the gas in the disk is not currently falling into the black hole, but rather orbits stably at its current radius. For material to move from the circumnuclear disk inward towards Sagittarius A requires loss of angular momentum, a slow process mediated by viscosity, essentially friction, magnetic field interactions, and gravitational torques from spiral patterns in the disk. Observations at radio and infrared wavelengths reveal that the circumnuclear disk is far from uniform. It contains several distinct clumps of molecules, each with different densities, temperatures, and velocities. These clumps might represent captured gas clouds or remnants of past events where material fell toward the galactic center. The northern and southern parts of the disk appear to have different motion patterns, rotating at slightly different speeds and possibly even in slightly different planes, suggesting they might have different origins. Perhaps they formed from separate gas clouds that fell in at different times. Within the densest parts of the circumnuclear disk, star formation appears to be occurring. Infrared observations reveal young stellar objects still partially hidden within their birth clouds. The fact that star formation can occur in the circumnuclear disk, despite its proximity to Sagittarius A, suggests that at least some regions of the disk are dense and self-gravitating enough, meaning their own gravity is strong enough to resist tidal disruption from the black hole. The inner edge of the circumnuclear disk is shaped by intense radiation from hot stars in the nuclear cluster. Ultraviolet photons from these stars ionize and heat the gas, creating a glowing boundary visible in radio observations. This ionized gas forms structures known collectively as the mini-spiral, a set of streamers of ionized gas that appear to spiral towards Sagittarius A. Despite their appearance, these streamers don't actually fall into the black hole. Instead, they represent gas that has been ionized and accelerated, but ultimately passes by the black hole on elliptical orbits, like comets swinging around the sunday. Over millions of years, the circumnuclear disk slowly feeds material toward the galactic center. Some of this gas will eventually reach Sagittarius A, either falling in directly or contributing to its accretion disk. But much of the gas may be blown away by stellar winds, consumed in star formation, or heated and dispersed by radiation from nearby stars before ever reaching the black hole. The balance between these processes determines how much material is actually available to feed the black hole and influences its activity level. Black holes grow by consuming matter. Yet Sagittarius A is remarkably underfed for a supermassive black hole of its size. Despite sitting at the gravitational center of a galaxy containing hundreds of billions of stars, swimming in an ocean of gas and dust, the black hole consumes matter at an extraordinarily low rate. Understanding what Sagittarius A eats, and more puzzlingly, why it eats so little, provides crucial insights into the life cycle of supermassive black holes and their complex relationship with their host galaxies. The primary source of food for Sagittarius A comes from stellar winds emitted by the massive stars in the central region. Hot, luminous stars constantly shed material in the form of fast-moving stellar winds, like the solar wind from our Sun, but far more intense. These winds carry significant amounts of mass, with massive stars losing perhaps a millionth of their own mass per year or more through this process. Collectively, the hundreds of massive stars in the central region provide a steady drizzle of material into the space around Sagittarius A. However, most of this wind material does not fall directly into the black hole. The stellar winds move at hundreds or even thousands of miles per second, carrying substantial kinetic energy and angular momentum. Much of this material shoots past Sagittarius A or goes into orbit around it rather than falling in. Simulations suggest that only a small fraction, perhaps a few percent, of the stellar wind material eventually makes its way into the accretion disk and ultimately crosses the event horizon. Current estimates suggest that Sagittarius A consumes approximately 1 Earth mass of material every few thousand years. To put this in perspective, the Earth weighs about 13,000 trillion pounds, 6 times 10 circumflex 24 kilograms. While that sounds like a lot, for a supermassive black hole it's essentially nothing. At this rate, Sagittarius A gains only about 1 solar mass, the mass of our Sun, every 3,000 years. Over the entire age of the galaxy, about 13 billion years, Sagittarius A has likely gained only a few 100,000 solar masses, through accretion a tiny fraction of its current 4.15 million solar mass heft. Occasionally, larger meals present themselves in the form of gas clouds drifting through the galactic center. These clouds are remnants of star formation, material ejected by dying stars, or pristine gas from the galactic disk. If a cloud ventures on a trajectory that brings it too close to Sagittarius A, the black hole's gravity can capture it, pulling it into an orbit that gradually decays. As a gas cloud approaches the black hole, tidal forces begin to stretch it. Imagine pulling taffy. The side of the cloud closer to the black hole feels stronger gravity than the far side, and this differential pull stretches the cloud into an elongated shape. Eventually, the cloud is torn apart completely, stretched into a long streamer of gas that spirals toward the black hole. The stretching heats the gas through compression and friction, causing it to glow in infrared and radio wavelengths. Over months or years, the disrupted cloud feeds into the accretion disk, temporarily increasing the black hole's brightness. In 2011, astronomers discovered what appeared to be a perfect opportunity to observe this process in real time. A mysterious object designated G2 was found to be approaching Sagittarius A on a trajectory that would bring it extremely close to the black hole. Initial observations suggested G2 might be a gas cloud with about 3 times the mass of Earth, moving at about 5 million miles per hour. Predictions indicated that G2 would reach its closest approach in mid-2014, passing within a distance where tidal forces should dramatically disrupt it. The discovery generated tremendous excitement throughout the astronomical community. Here, finally, was a chance to watch a real-time feeding event to observe how Sagittarius A would respond to an influx of fresh material. Many astronomers predicted that as G2 approached, tidal forces would stretch it into a long streamer, heating it to millions of degrees and causing it to emit brightly in X-rays and other wavelengths. Some predicted a dramatic brightening of Sagittarius A itself, perhaps increasing its luminosity by factors of 100 or more as the disrupted cloud material fell into the accretion disk. Telescopes around the world prepared for the show. Major observatories in Chile, Hawaii, and space-based X-ray telescopes all scheduled intensive observing campaigns around G2's predicted closest approach. Theorists ran simulations, making detailed predictions about what should happen. The press picked up the story, with articles speculating about a spectacular cosmic feast about to unfold at the center of our galaxy. As 2014 approached, observations intensified. Astronomers tracked G2's motion, watching as it accelerated toward its close encounter with the black hole. The object appeared to be elongating, stretched by tidal forces, just as predicted. But as the moment of closest approach arrived, something unexpected happened, or rather, didn't happen. The anticipated fireworks never materialized. Sagittarius A did show some increased activity in X-rays and other wavelengths during 2014, but nothing remotely like the dramatic outburst many had predicted. The black hole's brightness increased by perhaps a factor of 2 or 3 at most, a modest bump barely distinguishable from normal variability. And G2 itself survived the encounter largely intact, continuing on its orbit past the black hole. While it had been stretched and partially disrupted, it remained a coherent object rather than being completely torn apart and consumed. The anticlimactic outcome led astronomers to reconsider the nature of G2. One possibility that gained favor was that G2 might not be a pure gas cloud at all, but rather a shell of gas surrounding a star. If a young, low-mass star were embedded within the cloud, its gravity would help hold the gas together, preventing complete tidal disruption during the closest approach. Observations in the years following 2014 supported this interpretation, revealing hints of a compact source within G2 that moved like a star on a well-defined orbit. Another intriguing possibility is that G2 was the product of a binary star merger. If 2 stars in the galactic center had recently merged, possibly within the past few hundred years, they could have ejected a shell of gas during the merger process. This gas, moving on the same trajectory as the merged star, would appear as a cloud but would have different properties than a simple diffuse gas cloud. This might explain why G2 didn't behave as expected during its close approach to Sagittarius A. Despite the lack of a spectacular show, the G2 encounter was far from a scientific failure. The event provided valuable data on how material behaves in the extreme gravitational field near a supermassive black hole. It demonstrated that even close encounters do not necessarily result in dramatic accretion events, helping to explain why Sagittarius A remains so dim despite the abundance of material in the galactic center. It also revealed that objects near the black hole can be more complex than they first appear, with stars and gas often intermixed in unexpected ways. While Sagittarius A is generally quiet, it is not entirely dormant. Observations have revealed that the black hole experiences frequent flares, sudden increases in brightness that can boost its luminosity by factors of 10 to 100 over the course of minutes to hours. These flares occur primarily in X-ray and infrared wavelengths, providing tantalizing glimpses of more energetic processes occurring close to the event horizon. X-ray flares from Sagittarius A were first definitively detected in 2000 using NASA's Chandra X-ray Observatory, though hints had been seen in earlier observations. These flares typically last for a few hours and increase the X-ray luminosity by factors of 10 to 50, occasionally even more. The flares occur unpredictably, with no obvious pattern or periodicity, though observations suggest they happen multiple times per day. Between flares, Sagittarius A settles back to its normal quiescent X-ray emission, dim but still detectable. The exact mechanism producing these X-ray flares remains debated, though several processes are likely involved. One leading explanation involves magnetic reconnection in the accretion flow. Imagine rubber bands stretched and tangled around the black hole, suddenly snapping and releasing their stored energy. The plasma near Sagittarius A is threaded with tangled magnetic field lines, and these fields can become stressed and twisted by the differential rotation of the disk. When the stress becomes too great, the field lines can suddenly snap and reconnect in a lower energy configuration, explosively releasing the stored magnetic energy. This energy heats electrons to extreme temperatures and accelerates them to relativistic speeds, close to light speed, producing the observed X-ray emission. Infrared flares are even more common and have been observed extensively from ground-based telescopes equipped with adaptive optics and sensitive infrared cameras. These flares appear as rapid brightening events in the near-infrared, sometimes varying on timescales of just a few minutes. The fastest variations set important physical constraints. For the brightness to change substantially in 5 minutes, the emitting region must be no larger than 5 light minutes across roughly 5 times the size of the event horizon. This means we are truly observing processes occurring just outside the event horizon in the innermost regions of the accretion flow. One of the most intriguing aspects of infrared flares is the detection of quasi-periodic oscillations in some events. The brightness doesn't just go up and down randomly, but shows a rhythm. During certain flares, the brightness varies in a way that suggests material orbiting the black hole at the innermost stable circular orbit, the closest stable orbit possible around a black hole. The observed oscillation periods, typically around 20 to 30 minutes, are consistent with material orbiting at or near this innermost radius, providing direct evidence that we're observing matter just moments before it crosses the point of no return. In 2019, astronomers observed an unusually bright series of flares from Sagittarius A, with infrared emission reaching levels never before recorded in modern observations. These exceptional flares occurred over several nights in May, with the brightest events reaching luminosities more than twice the previous observed maximum. The flares were followed by additional brightening events over subsequent weeks, suggesting a period of enhanced activity that lasted for months. The cause of this unusual activity remains uncertain. The timing, roughly 5 years after G2's closest approach, led to speculation that the two events might be related, though the connection is not obvious. It's possible that material from G2 or from its surrounding envelope finally reached the accretion disk after a delay of several years. Alternatively, the increased activity might have been triggered by a completely unrelated event, perhaps the capture of a smaller gas cloud or an enhancement in the stellar wind feeding from nearby massive stars. While Sagittarius A appears quiet and dim today, multiple lines of evidence indicate that it underwent periods of much more vigorous activity in the past. The black hole we observe is caught in a quiescent phase, a cosmic calm between storms. Looking back through time, by examining the fossil remnants of past outbursts and using clever techniques like light echoes, astronomers can reconstruct a more violent history. The most spectacular evidence for past activity comes from the Fermi bubbles, discovered in 2010 when NASA's Fermi Gamma Ray Space Telescope conducted deep surveys of the galactic center region. These enormous structures extend roughly 25,000 light-years above and below the galactic plane, comparable to the distance from our solar system to the galactic center itself. To put this scale in perspective, if you could see the Milky Way edge-on from outside, these bubbles would be among its most prominent features, dwarfing the visible disk of stars. The bubbles emit gamma rays, the highest energy form of light, and they have surprisingly sharp, well-defined edges despite their immense size. The leading explanation for the Fermi bubbles invokes a major outburst from Sagittarius A approximately 6 to 10 million years ago, recent by cosmic standards, but long before humans evolved. During this event, the black hole likely consumed a massive quantity of gas, perhaps a giant molecular cloud containing millions of solar masses worth of material, or possibly a whole sequence of smaller clouds consumed over an extended period. The resulting feeding frenzy would have caused Sagittarius A to shine millions or even billions of times brighter than it does today, temporarily transforming it into an active galactic nucleus similar to those seen in distant quasars. The intense radiation and possibly powerful jets from this active phase drove shockwaves into the surrounding gas, heating it and accelerating particles to extreme energies. These shocks inflated enormous bubbles of hot, energetic gas that punched through the galactic disk and expanded into the halo surrounding our galaxy. Over millions of years, the bubbles continued expanding and cooling, eventually reaching their current size. Today, they persist as faint glows in gamma rays, visible only to specialized space telescopes, but serving as fossil evidence of ancient violence at the galactic center. Giant molecular clouds in the galactic center region also bear signatures of past illumination by intense radiation from Sagittarius A. Some of these clouds are glowing in ways that require them to be energized by X-rays far more powerful than what Sagittarius A currently produces. These are light echoes, a phenomenon where we observe radiation that left Sagittarius hundreds of years ago, traveled to distant clouds, and was reflected or scattered, only now reaching Earth after this longer journey. Light echoes work like ordinary sound echoes, but with light traveling across vast distances. Imagine Sagittarius A experienced a bright flare or extended period of enhanced activity several hundred years ago, perhaps around the time Columbus was sailing to the Americas. The intense radiation from this event spread outward in all directions at the speed of light. Some of this radiation traveled directly to Earth, arriving centuries ago when no telescopes existed to observe it. But some radiation traveled to distant molecular clouds, where it was absorbed and re-radiated or scattered, sending it on a longer path toward Earth that is only now bringing it to our detectors. By carefully mapping which clouds are glowing and how brightly, astronomers can reconstruct the brightness history of Sagittarius A over the past few centuries. These studies indicate that the black hole was significantly more active just a few hundred years ago, perhaps around the year 1600, possibly 1,000,000 times brighter than today. What triggered this past activity remains uncertain, but the light echoes provide a unique window into the recent history of our galaxy's central black hole. For decades, imaging a black hole directly seemed like an impossible dream. The event horizon of Sagittarius A, while enormous by terrestrial standards at 12 million miles across, appears incredibly tiny when viewed from Earth 26,000 light-years away. The apparent angular size is just 52 micro-arcseconds, roughly equivalent to viewing an orange sitting on the moon from Earth or trying to see a dime in Los Angeles from New York City. No single telescope, even one placed in space, could possibly achieve the resolution needed to image something so small. The solution, bold and audacious, came from a technique called Very Long Baseline Interferometry, or VLBI. Instead of building one impossibly large telescope, VLBI networks link multiple radio telescopes across vast distances, combining their signals to create the effect of a single telescope with an aperture equal to the distance between them. The resolution achieved depends not on the size of the individual dishes, but on the maximum separation, called the baseline, between telescopes in the array. If you could spread radio telescopes across an entire continent, you could create a continent-sized virtual telescope. If you could place them on different continents, you could achieve even higher resolution. And if you could coordinate telescopes all around the globe, observing simultaneously and combining their signals afterward, you could create an Earth-sized telescope with resolution approaching the theoretical limits needed to image a black hole. This was the audacious goal of the Event Horizon Telescope project, an international collaboration that would push radio astronomy to its absolute limits. The Event Horizon Telescope, or EHT, brought together a global network of radio observatories, each equipped with sensitive receivers capable of detecting faint radio signals. The network included facilities in Chile, Spain, Hawaii, Mexico, Antarctica, Arizona, and several other locations. Together, these observatories formed a virtual telescope nearly the size of Earth, the largest telescope ever built, though it exists only as a network rather than a physical structure. The observations themselves were extraordinarily complex. All telescopes in the array had to observe the target simultaneously, requiring careful coordination across different time zones, weather conditions, and local regulations. Each telescope recorded not just the brightness of the incoming radio waves, but also their phase, the position of the wave crests and troughs, with extraordinary precision. This required atomic clocks at each site, accurate to better than a billionth of a second. Think of it like trying to catch a single musical note played by an orchestra spread across the entire planet, where every instrument must be perfectly synchronized despite being thousands of miles apart. The weather posed a constant challenge. Radio observations at millimeter wavelengths are extremely sensitive to water vapor in the atmosphere. A cloudy day could ruin observations at one site, breaking the chain of the global array. The team had to wait for nights when weather conditions were favorable at all participating sites simultaneously, a rare occurrence that required careful planning and a bit of luck. They had only brief windows of opportunity each year when all sites could observe together, making every clear night precious. The data rate was phenomenal, far exceeding what could be transmitted over the internet in real time. Each telescope was essentially taking a continuous ultra-high-definition video of the radio sky, but capturing not just brightness, but the phase of radio waves with exquisite precision. Instead, each telescope recorded its observations on high-capacity hard drives, generating several petabytes of data per observing run. 1 petabyte equals 1 million gigabytes, enough to store about 250,000 DVDs, or about 500 years of continuous HD video. These weren't ordinary computer hard drives, but specialized systems designed for this extreme data rate. After the observations concluded, These hard drives were physically shipped to central processing facilities where supercomputers spent months correlating the signals from different telescopes, combining them to reconstruct images. Why ship hard drives instead of using the internet? Because the data was so massive that physically flying hard drives across oceans was actually faster than transmitting the data electronically. The data processing alone was a monumental computational challenge, requiring sophisticated algorithms to account for Earth's rotation, atmospheric effects, and instrumental delays. Teams of computer scientists worked alongside astronomers to develop new algorithms capable of handling this unprecedented data challenge. The EHT team had two primary targets from the beginning: the supermassive black hole at the center of the giant elliptical galaxy M87 and our own Sagittarius A dot. While Sagittarius A was in many ways the ultimate prize, it's our black hole. After all, it turned out that M87's black hole was actually easier to image and would be revealed to the world first. M87's central black hole is an absolute monster, containing about 6.5 billion solar masses, more than 1,500 times more massive than Sagittarius A. The galaxy, M87, lies about 55 million light-years away in the Virgo cluster of galaxies. Despite being much more distant than Sagittarius A, the enormous mass of M87's black hole means its event horizon is proportionally larger, and remarkably, the two black holes appear roughly the same angular size on the sky when viewed from Earth. The key advantage of M87's black hole for imaging was its stability. Due to its enormous mass, material orbits the black hole relatively slowly. Even at the innermost stable orbit, just outside the event horizon, gas takes many hours to complete one lap. This means that during a night of observing, the black hole's appearance remains essentially constant, simplifying the image reconstruction considerably. On April 10, 2019, in coordinated press conferences held simultaneously around the world, the Event Horizon Telescope collaboration revealed humanity's first image of a black hole. The image showed M87's black hole as a bright ring of glowing orange-red light surrounding a dark central shadow. The ring was not perfectly symmetric, but showed a distinct asymmetry, brighter on one side than the other, exactly as predicted by decades of theoretical modeling. The announcement made headlines around the world. The image appeared on front pages of newspapers, dominated social media feeds, and led television news broadcasts globally. It became one of the most iconic scientific images of the 21st century, comparable in cultural impact to the first photographs of Earth from space or images from the Hubble Space Telescope. The image was both beautiful and profound, direct visual confirmation that black holes are real, that event horizons exist, and that Einstein's general relativity accurately describes these most extreme of cosmic objects. But the EHT team had always intended to image Sagittarius A as well, and in many ways this was the more important target. While M87's black hole was spectacular and scientifically valuable, it was far away and had little direct connection to human civilization. Sagittarius A, however, is our black hole, the gravitational anchor of our home galaxy, intimately connected to the history and evolution of the Milky Way and, by extension, to the formation of our solar system and the development of life on Earth. The technical challenges of imaging Sagittarius A were considerably more daunting than for M87. The fundamental problem is variability. Sagittarius A is much less massive and material orbits it much more quickly. Gas in the innermost regions, just outside the event horizon, whips around the black hole with orbital periods of just minutes. Hotspots that might last for hours or days in M87's accretion disk appear and disappear in minutes around Sagittarius A. The black hole's appearance changes dramatically, even during a single night of observations, like trying to photograph a hummingbird in flight versus photographing a statue. This created enormous difficulties for image reconstruction. Traditional VLBI techniques assume that the source being imaged is essentially static during the observation. For M87, this assumption was valid. For Sagittarius A, it was completely invalid. Trying to create a single static image from observations that span hours, when the source is changing every few minutes, is like trying to take a clear photo of a running child who won't hold still. The solution required developing entirely new data analysis techniques. Instead of trying to create a single static image, the team had to model how the emission varied with time, essentially creating a movie of the black hole. But with observations taken at just a handful of snapshots throughout each night, and with the source changing faster than could be fully sampled, this was extraordinarily challenging. It required sophisticated statistical techniques, machine learning algorithms, and extensive use of computer simulations to test different analysis approaches. The analysis took 3 years of intensive work by teams of researchers around the world. The delay was partly due to the COVID-19 pandemic, which disrupted scientific collaborations and made it difficult for team members to meet and work together. But the bigger challenge was simply the complexity of the analysis itself. The team developed multiple independent imaging pipelines, different computer programs using different mathematical approaches, used different algorithms and assumptions, and cross-checked results extensively to ensure that the features they were seeing were real and not artifacts of their analysis methods. Finally, on May 12, 2022, 3 years after unveiling the M87 image, the Event Horizon Telescope team held another set of coordinated press conferences to reveal their second target. Sagittarius A. The wait had been worth it. The image showed our galaxy's central black hole as a bright, somewhat fuzzy ring of glowing emission surrounding a dark central shadow, similar in general appearance to M87, but with its own distinctive character. The announcement was a profound moment in astronomy, and indeed in human history. For the first time, humans could see the black hole at the center of our own galaxy. After decades of inferring its presence from stellar orbits, after years of detecting its radio and X-ray emissions, after building one of the most sophisticated observational instruments in history, specifically for this purpose, we finally had a direct image. The invisible had been made visible. The black hole that anchors our galaxy, that has shaped its evolution for billions of years, was no longer entirely hidden. Several theories exist for how supermassive black holes form. Perhaps they grew gradually over billions of years, starting from smaller seed black holes left over from the first generation of stars in the early universe. These seeds would slowly accumulate mass by consuming nearby gas and merging with other black holes, gradually growing into the supermassive monsters we see today. Alternatively, in the chaotic early universe, massive gas clouds might have collapsed directly into supermassive black holes without ever forming stars. The truth likely involves a combination of these processes, with different supermassive black holes having different formation histories. Regardless of how they form, supermassive black holes share certain fundamental properties with their stellar mass cousins. They have event horizons from which nothing can escape. They warp space-time dramatically. They can consume matter from their surroundings, and when they do, they shine brightly as the infalling material heats up and emits radiation. Remarkably, the physics governing black holes is quite simple. A black hole is completely characterized by just 3 numbers: its mass, its electric charge, which is almost always negligible, and its angular momentum or spin. The image showed a glowing ring approximately 52 micro-arcseconds across, matching theoretical predictions with remarkable precision. The ring represents emission from hot gas orbiting just outside the event horizon at speeds approaching the speed of light, heated to billions of degrees by friction and magnetic field interactions. The light from this gas is gravitationally lensed by the black hole bent around the curve of space-time like light bending through a magnifying glass, making the ring appear larger and brighter than the emitting region actually is. At the center of the ring lay the shadow, a dark region roughly 2.6 times the size of the event horizon itself. This shadow is not the event horizon, which emits no light and is invisible by definition. Rather, the shadow represents the photon sphere, a region where light can orbit the black hole before either falling in or escaping to infinity. Photons emitted inside the photon sphere are trapped, spiraling inward to cross the event horizon. Only photons emitted outside this radius can escape to reach our telescopes. The result is a dark shadow that reveals the location and approximate size of the event horizon. The ring was not perfectly uniform. It showed bright spots and dimmer regions, indicating that the accretion flow around Sagittarius A is clumpy and asymmetric. The material orbiting the black hole is not smoothly distributed, but instead contains overdense regions, hotspots that shine more brightly. The asymmetry is further enhanced by relativistic effects. Material moving toward us appears brighter due to a phenomenon called Doppler beaming, where radiation is concentrated in the direction of motion, while material moving away appears dimmer. Because Sagittarius A varies on such short timescales, the image released by the EHT team was actually an average of thousands of individual images created using different analysis techniques and different subsets of the data. By comparing images produced with completely independent methods, the team could identify which features appeared consistently and were therefore likely to be real, versus which features varied between analyses and might be artifacts. The bright ring and dark shadow appeared in every analysis, providing confidence that these were genuine features of Sagittarius A. The size of the shadow depends primarily on the mass of the black hole and is relatively insensitive to the details of the accretion flow or magnetic field configuration. This makes it an excellent tool for measuring black hole mass independently of other methods. By carefully measuring the shadow diameter in the EHT image and accounting for our distance to Sagittarius A, astronomers could determine the black hole's mass. The result: 4.15 million solar masses with just a few % uncertainty, agreed beautifully with the mass determined from decades of tracking stellar orbits. The convergence of two completely independent measurement techniques provides powerful validation for both methods and strong confirmation that Sagittarius A is indeed a black hole. What the image cannot and does not show is the event horizon itself. The event horizon is a boundary in spacetime, not a physical surface that emits light. It is defined as the region from which light cannot escape to reach distant observers. Everything visible in the EHT image comes from gas orbiting outside the event horizon. The darkness in the center tells us where the horizon is, inferring its presence from the absence of emission, but we can never directly observe the horizon itself. It remains forever hidden, cloaked in the perfect opacity that is the defining feature of black holes. From a mysterious radio source detected in 1974 to a direct image revealed in 2022, Sagittarius A has been transformed from an invisible phantom into one of the most intensively studied objects in all of astronomy. This journey of discovery spans nearly 5 decades, involving hundreds of scientists from dozens of institutions across the globe, countless nights of observation, and the development of new technologies pushing the boundaries of what's possible. What began as speculation about a possible black hole at the galactic center, met with skepticism and uncertainty, has become established fact, supported by overwhelming evidence from multiple independent lines of observation. The patient decades-long tracking of stellar orbits, the detection of relativistic effects during close approaches to the black hole, and finally, the direct imaging of the shadow cast by the event horizon have built an ironclad case. Sagittarius A is real. It is a supermassive black hole containing 4 million solar masses. It anchors our galaxy just as similar black holes anchor countless other galaxies across the observable universe. The black hole at the heart of the Milky Way has taught us profound lessons about the nature of physical reality. It has confirmed Einstein's general theory of relativity in one of the most extreme and intense gravitational environments accessible to human observation, where space-time itself is bent and twisted nearly to the breaking point. Every prediction Einstein made, gravitational redshift, orbital precession, the bending of light, time dilation, has been confirmed with increasing precision. The theory, developed over a century ago by a single person working with nothing but pencil, paper, and pure thought, has withstood every test we've thrown at it. It has demonstrated conclusively that black holes, once dismissed by many physicists as mathematical curiosities unlikely to exist in nature, are not only real, but common throughout the universe. We now know that virtually every large galaxy harbors a supermassive black hole at its center. These objects, far from being rare cosmic oddities, are fundamental players in the story of cosmic structure. And it has revealed deep connections between supermassive black holes and their host galaxies, showing that these cosmic monsters play crucial roles in galaxy formation and evolution. The mass of a galaxy's central black hole correlates tightly with properties of the galaxy itself, suggesting a deep, still not fully understood relationship between black holes and the galaxies that host them. Yet for all we have learned, Sagittarius A continues to guard many secrets. Deep questions remain about the fundamental nature of black holes, particularly what lies beyond the event horizon in the regions forever hidden from view. What happens at the singularity, where our equations predict infinite density and infinite curvature? Does the singularity actually exist, or does some unknown quantum effect intervene at the smallest scales? What happens to the information that falls into a black hole? Is it truly lost forever, or is it somehow preserved in ways we don't yet understand? The information paradox, the apparent conflict between general relativity and quantum mechanics, when applied to black holes, remains one of the great unsolved problems in theoretical physics. General relativity says that information falling into a black hole is lost forever, erased from the universe. But quantum mechanics insists that information cannot be destroyed, only transformed. Both theories have been tested extensively and both appear to be correct within their domains. Yet they make contradictory predictions about black holes. Resolving this paradox may require a revolution in our understanding comparable to the development of quantum mechanics and general relativity themselves, a theory of quantum gravity that successfully merges these two pillars of modern physics. Some physicists have proposed radical solutions. Perhaps information isn't lost, but is encoded on the event horizon itself, like a hologram storing three-dimensional information on a two-dimensional surface. Perhaps black holes slowly leak information through a process called Hawking radiation, named after Stephen Hawking, who predicted that black holes should very slowly evaporate by emitting particles. Perhaps the interior of a black hole connects to other universes or to distant regions of our own universe through structures called wormholes. Or perhaps our understanding of space-time itself is incomplete, and black holes are telling us we need new concepts we haven't yet imagined. As we look to the future, new instruments and techniques promise to reveal even more secrets of the galactic center. More powerful telescopes, both on the ground and in space, will track stars on ever closer orbits around the black hole, perhaps eventually detecting stars that complete an orbit in just a few years rather than S2's 16 years. These stars, orbiting even deeper in the gravitational well, will provide even more stringent tests of general relativity and could potentially reveal deviations that might hint at new physics. The Event Horizon Telescope continues to improve. More telescopes are being added to the global network, increasing its sensitivity and resolution. New observing techniques are being developed to capture how black holes change with time, creating movies rather than static images. Future observations might reveal the detailed structure of magnetic fields near the event horizon, or capture the moment when material crosses the point of no return, or detect the spin of Sagittarius A with high precision. Space-based gravitational wave detectors, currently in development, may catch the unmistakable signal of a stellar mass black hole or neutron star spiraling into Sagittarius A, providing entirely new insights into strong field gravity. When such an event occurs, and it's only a matter of time, the gravitational waves will carry information about the space-time geometry near the event horizon that we can't obtain any other way. These waves will tell us about the black hole's spin, its mass, and perhaps reveal subtle features predicted by general relativity but never before observed. Improved computer simulations will help us understand the complex physics of magnetized accretion flows and the intricate dance between black holes and their surroundings. As computing power continues to grow, simulations can include more physics, run at higher resolution, and make increasingly detailed predictions that can be compared with observations. These simulations are becoming virtual laboratories where we can experiment with extreme physics impossible to test anywhere else. Will Sagittarius A awaken again? Almost certainly, though predicting when is essentially impossible. If a large gas cloud happens to fall toward the galactic center on just the right trajectory, or if a star wanders too close and is tidally disrupted, we could witness a dramatic feeding event even within human lifetimes. Statistically, a tidal disruption event should occur every few tens of thousands of years, so we're overdue based on simple probability. When it happens, astronomers worldwide will scramble to observe it with every available instrument. More dramatically, when the Milky Way collides with the Andromeda galaxy in about 4.5 billion years, a certainty, as both galaxies are approaching each other at about 68 miles per second, the gravitational chaos will almost certainly funnel vast amounts of gas toward both galaxies' central black holes, triggering powerful active phases for both Sagittarius A and Andromeda's black hole. The collision won't involve stars crashing into each other. Space is mostly empty, and stars are tiny compared to the distances between them, but the gas clouds will collide violently, shocking and compressing them. This collision will trigger spectacular bursts of star formation and feed enormous amounts of gas to both black holes. For millions of years, both Sagittarius A and its counterpart in Andromeda will blaze as quasars, pouring energy into their surroundings at rates millions of times higher than today. The radiation will ionize gas across both galaxies, potentially affecting star formation for hundreds of millions of years. If any civilizations exist in either galaxy at that time, they will witness their night skies transformed by the brilliant active galactic nucleus at the center, a beacon visible even in broad daylight. In that distant future, the two black holes will themselves eventually merge, spiraling together over hundreds of millions of years and finally colliding in one of the most energetic events possible in the universe. The merger will release more energy in gravitational waves than all the stars in both galaxies combined emit as light over millions of years, and it will create a single, even more massive black hole at the center of the merged galaxy, sometimes called Milky Way by astronomers with a sense of whimsy. The gravitational waves from this merger would be detectable across the universe, a cosmic announcement that two giants have become one. But that apocalyptic event lies so far in the future that worrying about it now seems absurd. The sun will have exhausted its hydrogen fuel and swelled into a red giant long before then, likely making Earth uninhabitable. Humanity, if we survive, will need to have found new homes among the stars. For the foreseeable future, the next millions or even billions of years, Sagittarius A will remain in its current quiescent state, a sleeping giant at the heart of our galaxy. The story of Sagittarius A is ultimately a deeply human story. It reflects our species' drive to understand the universe, to push beyond the boundaries of the visible and the known, to comprehend nature at its most extreme and exotic. It reminds us that we live in a universe of wonders, where black holes lurk at the centers of galaxies, where the fabric of space-time itself can be bent and twisted, where matter can be compressed to infinite density and time itself can slow to a crawl. And it demonstrates that through the patient application of human intelligence, ingenuity, and collaborative effort across cultures and continents, even the deepest cosmic secrets can eventually be revealed. This achievement required international cooperation on an unprecedented scale. Astronomers from Europe, North America, South America, Asia, and even Antarctica worked together, sharing data, expertise, and insights. Political borders and national rivalries meant nothing compared to the shared goal of understanding our universe. The project involved physicists, engineers, computer scientists, and mathematicians, each bringing their unique skills to solve pieces of the puzzle. It required both brilliant individual insights and massive collaborative efforts, a reminder that the greatest human achievements often come when we work together toward common goals. The technologies developed for studying Sagittarius A have found applications far beyond astronomy. Atomic clocks, adaptive optics, interferometry techniques, and data processing algorithms originally developed for black hole research now benefit fields ranging from telecommunications to medical imaging to GPS navigation. The pursuit of pure knowledge, asking questions simply because we want to know the answers, has a way of generating practical benefits we couldn't predict in advance. 26,000 light-years away, Sagittarius A continues its silent vigil at the heart of the Milky Way. It has been there for billions of years, quietly shaping the evolution of our galaxy. It will remain for billions more, long after our sun has exhausted its fuel and Earth has become uninhabitable. We may never visit it physically, may never cross its event horizon, may never see directly what lies within its deepest interior. The distances are too vast, the dangers too extreme, and the physics too unforgiving. But we can observe it, study it, learn from it. We can decode the messages carried by light that has traveled for 26,000 years to reach us. We can track the dance of stars around an invisible partner and deduce the mass of that partner with exquisite precision. We can capture the shadow of an object that emits no light. We can test the fundamental laws of physics in conditions so extreme they exist nowhere else within our reach. And in doing so, we take one more step in humanity's greatest journey, the quest to understand the cosmos and our place within it. The invisible monster at our galaxy's heart has finally been seen. And in seeing it, we see ourselves and our universe more clearly than ever before. We see that we are part of something vast and ancient, that we inhabit a universe rich with wonders, and that the human capacity for curiosity and understanding can illuminate even the darkest corners of space. The journey of discovery continues, and Sagittarius A, that invisible heart of our galaxy, continues to teach us, inspire us, and remind us of how much we have yet to learn.